Alright, hello AP Physics students, and welcome to this video lecture, which is going to be going through how we can actually apply Newton's first law, Fig Newton's first law, to actual real-world scenarios. Before we get into that, though, I want to make sure that we're on the same page in terms of how we record forces, and namely that the units of force are these things called newtons, and we just abbreviate those with an N. Now, a newton actually stands for a kilogram meter per second squared, and I'm not going to get into this right now. That's going to make more sense as we move on through this unit on forces. However, I just want to present that to you so it's not goofy looking in the future. Now, one other thing that I want us to be sure that we're on the same page with is that forces are vector quantities. Forces are vector quantities. Because not only do we depend on the size of the force, we want to know how much force is actually there, but we also want to know which direction that force is acting. Okay, so those are the two big things that I want us to be on the same page with before we get into how we can actually apply Fig Newton's first law. So when we actually think about Newton's first law, we know that we have balanced forces, and we know that objects are going to want to keep doing what they're already doing because of those balanced forces. And we can call those situations where objects want to keep doing what they're already doing because of those balanced forces, we can call those equilibrium situations. We can get even fancier, and we can call this static equilibrium. So static equilibrium situations just mean that we have those balanced forces, and we can analyze those forces because we know that there is no external unbalanced force acting on whatever object we're dealing with. Okay, now to analyze these static equilibrium problems, what we have is we have these things called equilibrium equations, where we say that the sum of all forces is equal to 0. What this means is that the sum of all forces is equal to 0. That means that we have balanced forces. Okay, now this is a pretty general equation here. We can actually break this equilibrium equation up a little bit more, and we can talk about the different directions that we have acting on that object. Now, I want you to think back to 2D motion. We had motion in the x and the y direction. Just like in dynamics, we can have forces in the x direction, and we can have forces in the y direction. Okay, so in these static equilibrium problems, in these equilibrium situations, we know that our forces in the x direction are going to equal 0 because they are balanced in the x direction, and we know that forces in the y direction are going to equal 0 because they are balanced in the y direction. Okay, so application of Newton's first law, we can analyze equilibrium situations or static equilibrium problems. We know that forces are balanced, therefore all the forces on that object are going to sum to 0. And this equilibrium equation can be broken down into the two different directions that forces can act. Okay, so the next couple slides are going to go through actual problems demonstrating how we use these equilibrium equations, so please follow along carefully. Alright, so to give you an idea of how we can use these equilibrium equations that were discussed previously, really simple scenario here. So we have a box, and it's moving at a constant velocity of 2 meters per second. The box is being pushed with a force of 30 newtons. We need to figure out what the force of friction acting on the box actually is. So whenever we analyze scenarios, we always want to draw a Freebody diagram. So we have our box. Now, first force that we can always draw is the force of gravity. It always acts downward. And we know that we have some normal force there to counteract gravity. Now, these two forces are equal, and frankly, we don't really have to worry about these forces in the y direction because we're solely focused on what that force of friction is that's opposing the box's motion. Okay, so we also know that we have a force applied here, and that's equal to 30 newtons, and we have some frictional force, and that's what we need to find. So we're going to use an equilibrium equation to find what the force of friction is. So summation of forces in our x direction, and that's going to equal 0. Well, we know that Fa is acting in our x direction, and we also know that we have frictional force acting in the x direction. Okay, so that's equal to 0. Now let's plug in what we know. We know Fa is equal to 30 newtons, and now we're subtracting force of friction from that. That's all going to equal 0. So we're going to end up getting then that our force of friction in this problem is equal to 30 newtons. Okay, so here's a really simple example of how we can utilize equilibrium equations to analyze a static equilibrium or an equilibrium situation. Alright, so this next sample problem, it looks very similar to the previous problem. However, now we know a few more pieces of information. We know that the weight of our box, or the force due to gravity on that box, is 30 newtons. But now, instead of that box being pushed at or being pushed perfectly horizontally, we're now pulling it with like a string or something with a force of 15 newtons at some angle, and that angle is 30 degrees. So this situation gets a little bit more complicated now. So to draw the free body diagram here, we know that we have our force due to gravity. We have some force of friction. We have some normal force. And we have this applied force. I'm just going to call this Fa. And we could call this, it'd probably be more appropriate to call this Ft because we're pulling it with some sort of rope or cable or something. Okay? Now, we always want to break stuff down into the x and y components. Okay? Here, all of these are in x and y except for this guy right here. So what can we do? Well, we can actually break this into components, specifically x and y components. So we're basically going to draw a triangle here. So I'm going to draw a line looking like that, and this is going to be ftx, okay, because this is in the x direction. And then I'm going to draw in another arrow, and this arrow is going to be fty. And this angle here is that angle that force is being applied, and that was 30 degrees. So now we need to find what force normal is. So we're just going to worry about our equilibrium equation in the y direction. So we're going to have f of y is equal to 0. And what do we have acting in our y direction? Well, we have force normal. We have Fty, and then we have our force of gravity. And this is all equal to 0. Now I want to extend this equation out a little bit. We don't know Fn, that's what we're trying to find. Fty, if we extend that out, that is going to be Ft, and just using our trig, we're going to be using the sine function. Okay, so this is going to be sine of 30, and then this is going to be minus 30 newtons. Okay, because we know that the weight of that box is 30 newtons. Okay, again, I'm going to extend this out even further. So I'm going to have Fn plus 15 times the sine of 30 minus 30 newtons, and that's going to be equal to 0. Now just rearranging this to solve for Fn, then we're going to get normal force is equal to 22.5 newtons. Okay, so this is a more complex problem where we're not dealing perfectly in the x direction or the y direction. We actually have to utilize some trigonometry down here to break that force into x and y components. Okay, now I could extend this problem out, and I could also ask you to find F of friction, okay, force of friction. I'm not going to do that. I would encourage you to try that. The answer that you should get if you do that problem would be around 13 newtons. Okay, so the only two forces that you have acting in the x direction, like if you were to write your equilibrium equation, you would have Ft of x minus force of friction, and this would all be equal to 0. So there's your start if we were trying to find what the force of friction is. So I hope that this tutorial showed you, or this video lecture showed you how we can actually apply Newton's first law with these static equilibrium situations where we know that forces are balanced, and because of that we can easily analyze those situations. So take care, physics students.